All right. Good morning, afternoon, or evening, everybody. This is your host, Jennifer Brennan, and I'd like to welcome all of you to the Accelerating Science Using Virtualized Data from PO.DAAC webinar. It is 2 p.m. Eastern Time, Eastern Daylight Saving Time, so we're going to go ahead and get started. And what I'll do first is begin today's webinar just with a few logistics. To ensure the best audio experience, all participants have been placed in silent mode, but if you have any issues or you have any questions, what we'd like for you to do is enter those into the Q&A panel rather than the chat. And you should see this on the right side of your screen, but if you don't see it, you can click on the 3 dots on the bottom right of your screen, and that should pull up your panel options, and then you can insert a check mark next to the Q&A panel. Okay. Today's webinar is being recorded. The recording will be posted online to YouTube within a week of completion. And what I will do on my end is, once completed, I'll send an email to all registrants and participants with a link to both the recording on YouTube and also the presentation slide deck used within today's webinar. As far as timing is concerned, today's webinar will be 1 hour and 15 minutes long, with an hour being allocated to the presentation and live demonstration, and a 15-minute question and answer period, which will begin after the presentation. Depending on the volume of questions received, we may extend the Q&A session, but we will have a hard cutoff of 3:15 p.m. Eastern Time. During today's event, we have 2 speakers. Our first and primary speaker for today's content is Dean Hens. Dean is the NASA Physical Oceanography Distributed Active Archive Center, or PO.DAAC, engineer for data and software system operations. He will kick us off today with an introduction to virtual datasets, their utility, and basic usage. And then from there, he'll provide a PO.DAAC Cloud Computing Cookbook virtual dataset Jupyter notebook demonstration on how to work with virtual data sets, and he'll show you how to benchmark the results from this demonstration. After that, we will transition to our second speaker for this afternoon, Ed Armstrong. Ed is the science system engineer at PO.DAAC and the project data engineer. He'll continue with a science use case, illustrating the usage of virtualized data and examining upwelling in the Gulf of Tehuantepec. And then what we'll do after that is we're going to transition back over to Dean, and he's going to discuss some things that users should keep in mind when they're using virtual data sets, and also what to keep an eye out for. After this, I'm going to open up the final optional polling questions, and then we'll transition directly to the question and answer period. Before I toss it over to Dean, I just wanted to cover a quick final note about the Q&A session. We'll try to answer all questions within the time allotted, but if we're not able to address your question during the Q&A period, our speakers will be able to follow up with you offline. And so with that, it is my pleasure to introduce today's first speaker, Dean Hens. Dean? And with that, Dean, I'm going to stop sharing my screen and then toss it over to you.
All right. Can you hear me all right?
I can. Thank you.
All right. You should see my screen, and you should see as I put it into slideshow, and then you should also be able to see as I switch between screens.
I do.
Cool.
Looking good. Thank you.
All right. Hey, everyone. Appreciate you joining. We are excited to present this new data access technology that we've been exploring at PO.DAAC. And we're hoping it'll make your life easier and more enjoyable. So this is work that I've been doing along with Ed Armstrong, Mike Gangle, and Celia O. We're all at PO.DAAC. So before we jump into the presentation, just a quick intro. If you're not familiar with PO.DAAC, we are the Physical Oceanography Distributed Active Archive Center. We handle all of NASA's physical oceanography and terrestrial hydrosphere data. We deal with data publication and access and user support. So on the left here is a bunch of the measurements and variables that we offer, and on the right is all of the projects that we support. So check out that slide later, or check out our website. So the agenda for today, as Jennifer mentioned, I'll start off with 10 minutes or so of motivation and introduction to this new technology. Then I'll cover a basic usage, cookbook resources. I'll go through a notebook, what you should start off using to get introduced to the technology and the Cookbook chapter that we have that is always going to be a good resource for you. And I'll talk about some benchmarking results. Then Ed will show a more advanced use case. And then I will wrap up with some tips, tricks, and resources and what's on the horizon. So before we get started, just so everyone has at least a very high level understanding of the Python packages that we're going to use, because we have explored this technology using Python so far, and we'll explore it with other coding languages as those become available. But so Xarray is going to be the most important package. We use it for opening and exploring the netcdf files. If you're not familiar with it, it's also got a lot of useful functionality in terms of subsetting and basic scientific computations, array and matrix computations. It works out of the box with DAAC and parallel computing. Earth Access, which was first started by NASA OpenScapes, is a great package for handling Earth data login credentials very easy. So we use that. And then NumPy is a bread and butter package in Python. It's NumPy arrays are these like fundamental, multi-dimensional array objects that can be used with most other math and science packages in Python. And then DAAC is the analog of NumPy, but when you're wanting to do larger than memory or parallel computing. All right. So motivation and intro to virtual data sets. What are they? How are they going to make your lives easier? Hopefully. So take, for example, a sea surface temperature data set that we host at PO.DAAC. It's from the Ostia project. It's a level 4 global gridded sea surface temperature data set, 1 day per file and global coverage per file. And let's say, we're interested in this region in the Pacific. This data set is over 15,000 files and is around 11 terabytes. So if you're trying to deal with this data set, for instance, programmatically in a Python script or Jupyter notebook, what are you going to do? Do you want to download, hundreds of gigabytes to terabytes of data? If you want to deal with the whole record, you also have to know the file names, the structure, stuff like that. And then if you do have it locally, then what are you going to do? Are you going to, do a for loop and have to deal with each file at a time? A little cumbersome. One real quick, just moving something over on my screen. The dream, right, is to be able to, in one line of code, just be able to open the data set in this nice netcdf looking object here. And, it's got all the timestamps already combined together. And that's what we want. That's what we're going for. There we go. So, for instance, if you've tried to use Xarray before, you know that using this line of code should do the trick, right? Open MF dataset, you pass it the list of all 15,000 files. But if you're not using parallel computing, good luck getting that to resolve. And if you are using parallel computing, I think I have seen it resolve, but it does take some computing power, and we're aiming for an even easier way. And so enter virtual data sets. And so I'm going to make an analogy to the table of contents of a book. So you take all your netcdf files of this data set, and let's say the red box represents the region or the part of the data file that represents your region of interest. And think of the netcdf files as pages in a book. Then accessing the data files in the traditional way would be like reading the book cover to cover just to get the sections you want. Whereas using a virtual data set is like having a table of contents in your book and being able to directly go to the parts you want. So the virtual data set itself is this small reference file, a single file, a few to tens of megabytes in size. And all you're going to need to know to access the entire data set is just a link to that virtual data set. So a lot of text I'm throwing at you now, but just to go over the utility of virtual data sets briefly. They're going to enable what's called analysis-ready cloud-optimized data. You're not going to worry about the underlying files. You just get to worry about entire data sets. This technology does work both in and out of the cloud, although there are limitations to using it out of the cloud, as I will go over. It's going to improve performance, reduce computational burden. We'll show some of the benchmarking results that we've done. And then it should simplify data integration and reproducibility. And what I mean by that is, you got this notebook and you're accessing all these data sets. It's going to be easy to do that. And then when you pass on that notebook or script to someone else, it should be easy for them to run that same workflow. All right. So now I'll get into actually using the virtual data set. What your first steps could be to using this. Let me see, where do I want to start actually? Okay, I'll start with this slide. So if you haven't been to PO.DAAC's Cookbook before, that's our online resource where we host all of our tutorials for various ways of accessing data and different data sets. And so I've got some links up here for you. This is the homepage to the PO.DAAC Cookbook. And then this is going to be the link to the particular Cookbook chapter on virtual data sets that we'll cover today. And then these are two different links, one to GitHub, one to the Cookbook for the starter notebook. And don't forget to cite the Cookbook if you use it. So I'm going to go over to the Cookbook now, and I'll be going back and forth between the starter notebook and the Cookbook. This is the chapter that we've stood up for using virtual data sets. You can either use the link that I provided in the slides, or you can also find it by going to the homepage of the PO.DAAC Cookbook and going to Advanced Cloud Optimized Data using virtual data sets. You also see the two notebooks that we'll be presenting today here. And everything that I present today is also in this PO.DAAC Cookbook, plus more. So you should definitely check it out. And so I'll go through the first 3 sections and then the last section, and then I'll go over these 4, 5, and 6 after eds. So this first section is everything I've just covered in the presentation already, just introducing virtual data sets. And so this section now, using virtual data sets, is where your starting point should be. So you've got a link to the starter notebook that I'll cover here. You also got a link to Ed's more advanced notebook. So jumping to that notebook real quick, I'm gonna start going through this, and then I'll kind of jump back and forth between the notebook and the chapter. So let's start off with this notebook. You're importing, some packages. These are all installable with pip or Mamba or Conda. And then the first thing that you're going to want to do is get your Earth Data login credentials, like you have to do with any Earth Data data access method. With the Earth Access package, it's just a one-liner. You input your credentials. And then the remainder of this code is just boilerplate code. You're not going to have to change it in any way. And in fact, we're hoping that this will one day be wrapped up into the Earth Access package. But it's just taking your Earth Access login credentials and wrapping them in this mapper and creating a pointer to the virtual data set. And the only thing that you're going to have to pass it is the link to the virtual data set. So let's open up a file section 2, open up and explore a file. So let's say I have my link to my virtual data set. And where can you find the virtual data set link? If you go back to the Cookbook chapter, currently it's in this available products section. If you go to that, we've got this table with the current data sets that have this virtual data set technology. You've got the links to the landing pages here, and then you've got the virtual data set links here. So you can just right click and copy the link and paste it into the notebook here. And then once you do that, the rest of the code to open up the data is all boilerplate. You're just going to use that get VDS mapper function that we defined in section 1. And then it will pass the output of that VDS mapper straight into Xarray's workhorse function open dataset. And none of these keyword arguments should need to be altered for any of the data sets currently. And with that, you get the full data set. So I forgot to mention, this is the Ostia sea surface temperature data set that I mentioned earlier in the slides. It's 15,000 files, 11 terabytes of data. And typically it takes more like 10 seconds, but in this run that I did, it took under a second. And like that, you've got a nice organized Xarray object with all of the data for the entire data set in it. This is, if you're not familiar with Xarray, this is what's called lazy loading. So I don't actually have like locally in my computer all 11 terabytes yet, but I do have these nice organized pointers to all the data. And at this point, there's nothing specific to virtual data sets. This is all just Xarray. So I can, look at my coordinates. I can look at my data variables. I can look at my, variable level attributes, my global level attributes. I can check out the time coordinate and see that it's going from 1982 to 2023. This is all just Xarray at this point. And so let's explore the data now. So this is all Xarray built-in functions to just select the first timestamp and then just plot a global map of sea surface temperature. You can see that takes a handful of seconds to do. Next, I'm going to do a little mini analysis. So I will take a 10 degree by 10 degree region off the US West Coast here where my mouse is. And I will compute the regional mean sea surface temperature for the first decade of the time record. So that's what I'm doing here. I'm defining the spatial and temporal bounds. And then this is Xarray built-in functionality to get that subset. This is a lazy loaded subset. You can see the time. There's fewer timestamps now. Going down here, this is the line of code to compute the average over the latitude and longitude dimensions. That took, for this run, it took me 4.5 minutes to do that. And then the remainder of this code is plotting the results. So yeah, get a regional mean average in a 4.5 minutes. Hope that piques your interest. The remainder of this section 2 is repeating that same workflow, but for 2 additional data sets just to give you guys a variety. So the second data set that I do it for is from the CCMP project, and it's ocean surface wind speed. So I'm just going to skip over that since it's the exact same workflow. You should check it out though. Here's the plot of the first timestamp, and then here's the plot of the first decade. And then the third data set that I do it for is Echo, which is an ocean model, 4D ocean model. And I do it for the ocean salinity variable at 5 meters depth. Same thing, plot the first timestamp and get the first decade mean time series. And then the last section of the starter notebook is for people who maybe don't want to use Xarray built-in functions for everything. So maybe just use the Xarray package for loading the data because it's so darn easy, but then you want to extract the underlying arrays from the Xarray object as NumPy or DAAC arrays, and then use it in whatever other package you want, or take a subset of the virtual data set and download it locally as a netcdf. So I won't go into this part in detail. It's pretty straightforward, but kind of the same idea. In this case, instead of using the sea surface temperature data set, I'm using the Echo ocean model salinity data. Same idea though, where I'm getting the virtual data set link from the Cookbook chapter table, use my function that I defined in section 1, and then load the data with Xarray. And in this case, it takes a handful of seconds. The time record is 25 years, 4-dimensional data set. I've got it here. Now this first subsection takes the first year of data and a spatial subset, and shows you how to get either a NumPy array for the salinity data or a DAAC array if you're trying to do parallel computing or larger than memory computations. And then the last subsection is if you want to download a subset of the data as a netcdf locally, again, get your subsets and I'll go back to this block in a minute, but yeah, you save the netcdf file locally, and then the remainder of the section is just showing you how to reopen the netcdf file and make some plots. One thing I want to mention is this big old block of code here. This is, you won't have to change anything in this. You just have to copy and paste it into your notebooks and scripts for now, but we're hoping it'll go away soon. Just in the creation of the virtual data sets with the particular version of the package we use, they produce some variable level attributes that the netcdf package doesn't really like, and so you kind of have to either remove them or reformat them. But all you need to know for now is just run this code. And certainly reach out to us if you have any questions. So the last thing I want to cover before I hand it over to Ed is some benchmarking results. So these benchmarking results are in the Cookbook chapter. What we did was we took that same analysis that I showed in the starter notebook, taking the regional mean time series over this window off the US West Coast. We did it for the 3 data sets that were in the starter notebook. So CCMP wind speed, ASTIA sea surface temperature, echo ocean salinity at 5 meter depth. We did this computation and we timed it for 1, 5, 10, 20 years and the full record. And we compared virtual dataset access methods to traditional methods of either streaming or downloading the native netcdf files. So these 3 plots are all qualitatively the same. So let's just look at the leftmost plot. And the horizontal axis is number of years analyzed, and vertical axis is total download plus analysis time. And the colored lines are virtual dataset access methods, whether you're in cloud versus out of cloud, whether you're using HTTPS versus S3 endpoints. And qualitatively, you can just compare them to the black lines, which are the native or the traditional methods of either streaming or downloading. And qualitatively, you can see the results. You get a performance improvement from using the virtual data sets. It's an order of magnitude or better. This red line, which represents using the virtual data set out of cloud, there's a reason why it doesn't go all the way to the full record, and I'll get to that later in the talk. The only other thing I want to mention for these benchmarking results is that if you do download the data locally, so we tried, downloading the data locally and then, working with the data locally, it is actually faster at that point. Then you just have to ask yourself if you want to download all that data. And so that's the end of that section, and I'll mute myself and then pass it over to Ed. But I will continue to drive.
All right. Well, hello, everybody. I'm Ed Armstrong. I'm going to talk about a science use case where we're going to look at an upwelling signature in the Gulf of Tehuantepec using these virtual data sets, many of the data sets that actually Dean already showed you. So next slide. The Gulf of Tehuantepec is this area off Mexico in the a little more context here. What I'm going to demonstrate is interdisciplinary analysis incorporating 4 unique data sets for SST, ocean wind, vertical velocity, and surface salinity. We've seen actually many of them already here in the past minutes. And what we're going to do is read and then regrid and resample them to common time steps so that we can do some overplotting and make some clever plots to explore the variability in time. This notebook is available on our GitHub site and accessible via the Cookbook as well. Next slide, please. So the Gulf of Tehuantepec is this area off the west coast of Mexico in the Pacific Ocean where you have these episodic events during the winter time where these winds get funneled from the Gulf of Mexico through these straddling mountain passes in Mexico and then shoot out over the Pacific Ocean, accelerate actually over land through these gap winds. into the Pacific Ocean and cause open ocean upwelling, wind-driven curl upwelling. So what we're looking at here is a schematic I found from a weather forecast from a wiki site that shows the wind as the wind barbs, and they're very strong in the when they first exit from the land into the ocean, but then they decelerate and they spatially change as well. And so there's areas of stronger winds and weaker winds that cause this open ocean wind-driven signal. Next slide, please. This is going to show you another cartoon that I found in the open literature that demonstrates what I'm talking about with regards to the wind stress curl, in contrast to the boundary-driven, or where you have a land boundary that's typically known. In this case, in the open ocean, where you have spatially variable winds, it changes. It changes spatially the Ekman transport, and thus we get open ocean curl-driven upwelling that's depicted here with these yellow arrows. So that's showing the vertical motion of the cooler water coming to the surface. And of course, if you have a land boundary, you have also coastally driven upwelling that's in the red boundary. But that's not the case that we have in this Gulf of Tehuantepec upwelling signatures. And we typically see this signal in the wintertime, is when these peak winds appear. So how strong are these winds? They're tens of knots, up to reports of 100 knots. So these are like hurricane typhoon strength winds, dramatic, very powerful winds that cause this upwelling signal. Next slide. Okay, so yeah, this is the SST ocean response from space. This is from our SOTO or World Viewer. This is the Muir Level 4 SST dataset, a daily gap-free dataset at 1 kilometer of SST. And this particular image shows January 13th, 2011. The wind forecast, I forgot to say that, was from January 11th. So this is 2 days after. And we see this very cool spot, this wind-driven upwelling spot appearing in the Pacific Ocean. This is in the Gulf of Tehuantepec region. Actually, when you look at the image, you see the evidence. If you look at the land, the evidence of the mountain ranges straddling each side of that cool spot in Mexico as the winds come from the Gulf of Mexico again and then accelerate out into the Pacific Ocean. So how strong is this cooling? Well, in this case, a particular image is up to 10 degrees. That's a lot of cooling, folks, and a very strong upwelling signature. Next slide. This just shows another image from another date, more recent date. Also, the SOTO viewer, the Muir SST. This is January 24th, 2025. So not quite as strong. What I'm showing here is the region of interest, the little box where we'll conduct this analysis. And that's just a 1 degree box, kind of what I thought was a sweet spot of the signature. And so as I'm going to demonstrate in the Jupyter Notebook, at the next step, we're going to load these virtual data sets and then resample in this region of interest to monthly 1 degree intervals. And so again, why do we do this? Because the data, otherwise the data when you overplot it is a little bit too noisy. So we need to resample to some more realistic time steps and spatial steps to be able to make some sense of the plots. We're also going to calculate the wind direction. That's not given to us natively. And then, of course, we're going to overplot these different time signatures and examine the relationships and look at the variability. And we're also going to generate a 41-year SST spatial sample mean in this area. All right, so I'm going to go ahead and take control and share my screen and work through a few of the notebook cells. Again, this is a Jupyter Notebook that's running locally on my system. And hopefully you can see that right now. This is the notebook you can find at our GitHub site today if you wanted to run it after the seminar. And the first couple images are what we've seen already, the SOTO view of the ocean cooling, the Gulf of Tehuantepec wind signature. And so, as I work through this thing, I'm not going to execute everything because some of these, especially the resampling and regridding steps, are very computationally intensive. And I'm not going to lie, they take some time even on a very powerful EC2, and I'm just running locally here the Jupyter Notebook on my laptop. But some of the key packages, of course, are going to be from Xarray, Xarray, and Earth Access. So we're using Earth Access, Xarray, and specifically we're using Xarray version 2 at this point. And so I'm going to load some of those packages, and then I'm going to execute my step to do the login with the Earth Access package. And of course, this establishes my login privileges to be able to get the endpoints in the NASA Earth Data Cloud. That works very fast. And because I have the username and password saved here locally, it doesn't prompt me for that. This is that VDS wrapper that Dean mentioned that to establish your file system and other AWS credentials. Once I have done all that, I can actually open up these data sets. So the first one is going to be the Ostia sea surface temperature. And we see the link to the data set. So again, this is the reference file, the virtual reference file, the very lightweight JSON. It's on the order of about 100 megabytes. And we're going to execute this cell and establish our file system. And now we're actually going to use Xarray to open it. And when I was running this, that's super fast. When I was running it this morning, I was getting less than 1/10 of a second. Now it took 263 milliseconds right here. So that's still pretty rapid. And this just shows we've haven't loaded all the data, of course, but we have access now to 11 terabytes of data. We know where all the references are located by reading the reference file. And the particular variables that we're going to be interested in is this one, analyze SST right here. So this is all typical Xarray output. We're going to be doing the same thing with the CCMP. This is a wind data set, a long time series wind data set. And so that took even faster, quarter of a second, and nearly a terabyte of information we have at hand right here. This particular data set does not have the wind direction. We would like to get the wind direction, and we can calculate that from the U wind and V wind variables, the north and south, east and west. So we'll go ahead and do that and add that to as an Xarray to the data set. And now we have wind direction. So now we're ready to do the analysis. And so this is the region we've selected. It's just a simple 1 degree region here, 1 degree by 1 degree box. We're going to be doing it just over 10 years. The SST record is 40 years. The wind record is nearly 30 years, but we're going to just take a slice, a 10-year slice of that. And this particular step, I'm not going to execute again because it's very computationally intensive. And it took a rather powerful EC2 to actually calculate this. And you see the wall clock time here is on the order of just under 4 minutes. So there are, when you start doing very computationally intensive things, that's something to be cognizant of, that things, just because you've lazy loaded the data set doesn't mean you can actually do things in a very rapid fashion. Say on your workstation or your home laptop. Okay, and the next step is another step. We're doing the resampling of the wind directions. I did forget to mention this actually resamples the SST and the wind speed on the common monthly 1 degree time steps and loads it into memory. And we're going to do the same thing for the wind directions. Once we've done that, we actually calculate upwelling favorable periods based on a direction of north to northeast and at least about 6.8 meters per second, just so that you'll see we can do some nice identification of when these upwelling periods occur. And then we're going to, once we have all that information loaded, we're actually going to execute this plot. And so this is the first result I'd like to share with you. This is the sea surface temperature signal overlaid with the wind speed. SST is in blue, the wind speed is in red. And the gray areas are the shading periods where we define the upwelling favorable periods based on wind direction and wind speed. And we've seen that the signals align very nicely. When the wind blows very strong on the order of 7 meters per second, we see these strong drops in the sea surface temperature. And these are these wintertime episodic Gulf of Tehuantepec wind events. And they always occur in the wintertime, as if you look at the y-axis right here that has the time in years. I've also overlaid the wind barbs that show the direction and the magnitude. I believe the thick barb just means it's at least 7 meters per second or something like that. And all this information, all this phenomena is all lining up very nicely as expected, almost as expected, right? When the winds blow strong, we get the cool open ocean driven upwelling. And the sea surface temperature drops as cool water replaces the surface water that's being affected away from our box. All right, so that's the SST and CCMP. We can also look at the ocean vertical velocity. So we're going to load the Echo Ocean Vertical data set. This is a daily half-degree data set. That's a terabyte of information right here. Also only took a few seconds to load. The variable of interest is going to be this vertical velocity here. We're going to conduct the same resampling exercise. I'm not going to actually execute this step But when we look at the plot of vertical velocity SST, we see a commensurate type of relationship where during these upwelling favorable periods that are again shaded, this is the same shade as we saw the previous plot, and the SST drops, you can see the vertical velocity that I've now highlighted it as a more bolded purple is positive. So when the vertical velocity is positive, that's when the water is going towards the surface. It's being upwelled, and that's what we see here in the bolded purple, that they align very nicely with these upwelling periods. All right, the last one we're going to be looking at is we're going to be looking at the temperature salinity, the echo ocean temperature salinity, and looking at the salinity signal. So we load that one up. And that, again, is a terabyte data set that only opened up in a few seconds. And there's some different variables in there. We're going to be looking at the salt variable, going to be doing the same resampling and the same overplotting. And in this case, so now we have salinity in orange. Something a little bit different is going on because the peak salinity, when the cool water that has a higher salinity is advected to the surface, brought to the surface, there appears to be a little bit of a lag. I mean, the salinity is still high when these shaded upwelling favorable periods occur, but the peak salinity is a little bit lagged. So not quite sure what's going on there. I'll circle back that to a little bit to that thought in my summary slides. All right, so that's it for the overplots. I did want to show you just a little live exercise of calculating a spatial mean plot right here. So what we're going to be doing is, let me just execute these two cells real quickly here, and then I'll go back and set up the problem. All right, so for the Aussie SSD data, which is a 40-year record, the plots that I showed only used 10 years of that, but now we're going to use all 40 years. What we're going to do is for the January, when we expect the peak cooling, kind of around the February, December timeframe, let's just pick the month of January, it's the peak. We're going to calculate over all the January data in the Ostia time series. We're going to calculate a mean and create a plot of that. Take a look at it. So in this case, we're going to do it over a 5 by 5 degree box, so a little bit bigger than the 1 by 1 degree box. And again, we're going to be doing that over all years, so from 82 to 2023. And so these are the steps where we lazy load the data. So we take the SSD_DS data set that we loaded before, and we're just going to, for the analyzed SST, we're just going to slice it with this particular latitude, longitude range, and time range, right? That's the lazy loaded bit. And then from that, we're just going to be taking the January time steps, so those daily data that fell within the month of data. And so this is, we're not actually loading any data in memory of this part, we're just getting reference to it, but we had over 1,300 time steps. So there were over 1,300 daily January data within that 41-year stretch. And then the next step is actually where we're going to calculate the spatial mean, where we take a mean over that subsetted SST month, and we're going to compute the mean and also subtract a constant to convert the degrees Celsius to temperature. So that's still running. Usually takes just a little over a minute to calculate. Let's just give it a few more seconds here. And then once we have this information, we're going to just create a fancy spatial plot and look at the data. All right, maybe there was a slight hiccup, so maybe I'll just skip this part. And
we could always
my last slide will be just the summary slide. Yeah, this was running fine, of course, before the meeting, but now appears maybe to get to some kind of bottleneck. So we sometimes see that from time to time. Again, I'm running locally here over home internet on my 3-year-old MacBook Pro, and I think we'll just punt at this point, Dean, and I'm gonna unshare, and we're going to go back to my final slide. So sorry about that, folks, but yeah, if you run this notebook, this will execute. Perhaps something went wrong. I'm gonna stop sharing now. All right, and so back to the presentation, please.
You should see it now.
Okay, so there we go. Next slide, please. Okay, so this is the summary plot or summary slide that shows the three plots overlaid. So just take another dive into it. So the first one is SST and wind. SST is common to all three of these plots, but the other parameters change. So the top one is SST and the ocean wind. The middle one is the SST and the ocean vertical velocity. And the last one is the SST and salinity. So again, yeah, the core, I guess finding of this particular little mini cursory investigation is that, yeah, when the winds are blowing and honking in that area of the Gulf of Tehuantepec, we see huge drops due to the open ocean upwelling, a signal that we expect and see and confirm from these two satellite-based objects. The next one shows the effect of the SST or the wind and the ocean response from the wind with respect to the vertical velocity, the upwelling velocity that again is bolded wherever it is positive, and it also aligns up very nicely with these upwelling favorable periods. But the salinity, the lower one, is a little bit offset. The peak salinity does not line up in the shaded area. So why is that? It could be maybe a model artifact. I didn't say before, but actually I'm using the first depth level from this model, and that's not right at the surface. It's actually at 5 meters, as you see in the legend. And so that could be effect too. It would be interesting to see, perhaps, to bring in a satellite-based ocean surface, an actual ocean surface salinity product that has been virtualized. We actually have one, but it didn't actually overlap this particular period of interest. But yeah, it would be interesting to overlap the model salinity versus the satellite observed salinity and the ocean response to see what's going on there. So yeah, I mean, the neat thing about these investigations, you can move these boxes, these spatial areas, and reconfigure these time steps to your desire very easily, and recompute these exercises. So other data sets to bring in here would be, of course, things like say an ocean color from Sea-West the Modus era, if such a thing existed, as well as the surface salinity, perhaps even ocean currents to see what other ocean responses to these wind events you could see in the data. All right, so I think I'll leave it right there and turn it back over to you, Dean. Thank you.
All right, thanks, Ed. You can all hear me still?
Yes.
Cool. Yeah, let us know if the computation completes. And I want to thank Mike. He's furiously answering all the questions in the chat. And I was reading some of them, and I think this next section is going to answer several of them. But just to clarify one particular question that was asked, to clarify, those notebooks that we showed can be run both inside and outside of the cloud, especially the starter notebook, which are smaller computations. You can run outside of the cloud as well, although there are some limitations to the size of computation that you can do outside of the cloud, and I'll get to that in this section. So I want to talk about scope of usability, which is precisely, that topic of what can you actually use these virtual data sets for on your, personal laptop, for example. Additional resources that are available to you, and future objectives at PO.DAAC for these virtual data sets. So first of all, scope of usability. There's a list that we have on the Cookbook chapter. Let's see where if I go back to the Cookbook chapter and go to the top, there's this guidance on scope of usability. So I suggest reading these bullet points a few times. It could save you a lot of headache in the future. These are lessons that we've learned. And in the presentation, I'm going to highlight just several of them. And the first is setting expectations for, how much data are you going to be able to crunch with these virtual data sets just on your personal laptop. So I like thinking of my personal laptop plus the virtual data set as a hummingbird, and the netcdf files in a data set as flowers on a bush. And as a hummingbird, you can zip from file to file very rapidly and get little parts of the data as you want. You can jump around any flower you want, but you're a hummingbird, you're small, you can only fit so much nectar, and so you can only analyze so much data at one time. If you want to analyze all the files and a larger fraction of all the files, you're going to need a flock of hummingbirds, and so you're going to have to scale up. either if you have like a local computing cluster you have access to, or if you want to scale up in the cloud and start up resources there. That's a topic that could be an entire other seminar. Second point, and I want to stress, is the limitations for using the virtual data sets when you're out of the cloud. We found when we were doing the benchmarking analysis that we hit a limit with the amount of data that we could access outside the cloud at once. It seemed to come from limitations to how many data requests that we can make at one time. And so I'm not sure if this will always be a limitation or not. But putting up this benchmarking plot that I showed from before, the red line, right, is the out of cloud virtual data access method, and that's the reason why it stops at 20 years. For that particular analysis, we couldn't make any more data requests than that. The number of years may be different for you depending on the complexity of your analysis. And then the last point I want to highlight in the talk is that these are not new data sets. These are all data sets that we've already hosted at PO.DAAC, and they're still there in all their NetCDF glory. These are just virtual layers over those. So if you're interested in the documentation or citations for the data sets, please consult the original data set landing pages and don't forget to cite them. All right, so resources that are available for you for further learning. Again, this is all going to be on the Cookbook chapter as well. We're using Xarray and DAAC currently. We will explore other packages like Xarray Python as time permits, but for now we know Xarray, and the documentation for that is really good. The more Xarray and DAAC that you know for parallel computing, the more power to you. And like I said, the documentation is very good. And so I've compiled a few links for you here, ranging anywhere from like introductory to Xarray to more advanced functionality of using Xarray plus DAAC for more extensive computations. So check those out. And then we also have I have some links that I've compiled for if you want to dive deeper into the virtual data set technology itself, including a high-level overview of the technology here, as well as the virtualizer package, which is the Python package we use to create the virtual data sets. There, read the docs page. And then if you want to try and create your own virtual data set, which is something I think I saw in the chat, you can give it a try. And we've posted on the Cookbook the workflow that we've been using to create our virtual data sets. So you can give that a try for any data set you want. No promises that it will work. They need to be formatted correctly, and that's part of what we've been exploring with this technology. So just another reminder that all the resources that I've just presented here are listed in the Cookbook. And then last section, future goals. Just want to stress that this technology is actively being developed, and so we are updating our workflows and our recommendations and our tutorial notebooks as the technology develops. So please check back often, and please also let us know if you run into any issues. We are very interested. Another future goal is to expand the variety of data sets that we're going to offer with this technology. And I think that was touched on in the chat. Someone asked the question about that. So we would love to start exploring level 2 products. That's like your satellite, that's your data along satellite swaths and orbits, data sets with multiple groups, forward streaming records, even combining data sets together into one like master data set. These are all things that we are exploring. And there was a question about ice chunk in the chat. We are looking into ice chunk as well. And then the last future goal that I'm highlighting here is integration of virtual data access straight into the Earth Access package. If you remember from the starter notebook, there was like that boilerplate block of code in the beginning, but we would like to absorb that and more into the Earth Access package and make it even easier just by knowing the dataset short name with the virtual data set that you want. Passing that into Earth Access, it should look something like this. All right, so that's the end of this talk. This is a summary slide. It is just reiterating the utility of virtual data sets from a previous slide. So I'll leave that for you all to come back to and reflect upon. But the utility of virtual data sets range from just making your life easier, accessing entire data sets, to increasing performance. Let's see. And some efficiencies that I do want to highlight, though, is there are several of them, right? Efficiencies in computation time, as we showed with the benchmarking, lines of code written, which I hope is evident from the notebooks, data downloaded. You're only downloading the portion of the data that you want, and that equates to dollars. And then my favorite, which is less physical energy used. So there's all this emerging technology, whether it's AI or other, scaling up in the cloud. And there's always this question of like, what's the actual physical energy cost, and how much energy are we using to increase, our computation times or improve them? And what I like about this technology is that it's a refreshingly clever way to access the same amount of data that you've always been accessing in just a much more efficient way, as far as I can see. And so I really like it from that standpoint. So I just want to give a shout out to a few people. I don't think I mentioned this, and I don't think it's a secret based off of your questions in the chat, but we're not the ones developing the virtual data set technology. We're just adopting it and bringing it to PO.DAAC. So people who are really key to us gaining our understanding of virtual data sets, first of all, Ayush Nag, who was a JPL intern, and his project was kind of the first look into virtual data sets for us at PO.DAAC. And then Ryan Abernathy and Joe Hammond at Earthmover, and Amy Barciaskis at Development Seed, and Luis Lopez at NSIDC. All of them were very knowledgeable and were very generous with their time in getting us caught up to speed and keeping up to date with virtual data set technology. So we appreciate them. And then the virtualizer team, which are creating the package that we actually use to create the virtual data sets, have always been super responsive whenever we open up GitHub issues. So I appreciate them for that. And then additional thanks to the NASA OpenScapes and the Earth Access community. It was through lots of talks with them that inspired kind of us figuring out how we want to incorporate virtual data sets into, our data archive structure. And then lastly, the Coil team. Since I've started at PO.DAAC, I've been using Coiled to get into the cloud and start up resources in the cloud, and they've made my life super easy so that I can focus on the things that I want to focus on. And so I really appreciate them. So if you have any questions, whether it's your science use cases, your dream data products, your troubleshooting issues, please reach out to us. Here's mine and Ed's emails, as well as some more general ways to contact us. And thank you for your time. I guess for now, I'll just leave it at this contact slide. And I guess hand it over to Jennifer.
Yes, perfect. Thank you so much. Thanks, Dean. All right. So I've opened up the final polling questions, and those will be open for around 20 minutes or so. And what we'll do now is there are a couple of questions in the chat that were not responded to earlier. So I'm going to start with those, and then we'll hop down to the Q&A, and I'll go over those questions that do not currently have a text response. All right. So a question, bear with me for 1 minute, if you will. I don't think this has been responded to. Does VDS work with NOAA data?
I'll take that. It's I'm assuming this question is going to come up a lot with like, do virtual data sets work with NOAA data? Do they work with other DACs? And the answer is, if the data sets are formatted well, and it's up to those organizations to create the virtual data sets. And so I think that is something we're excited to do, is to start working with other organizations like NOAA and other DACs and figure out, past. I know they've been working on it, but the answer is, it's their prerogative to do that. I hope that answered it.
Thank you, Dean. All right, and I'm just scrolling down to see which questions have not been answered yet here. All right, so in general, what makes it a virtual data set?
I guess just that's what they um I don't know exactly what you're getting at, but that's just like the terminology that I guess came up. I guess it's in a way, it's right. We're not like reproducing, you got your netcdf files, and we're not like reproducing another data set that's just like all the data combined into one massive netcdf file. It is just this lightweight few megabyte JSON file that kind of points to all the netcdf files. So I guess in that sense, it's like virtual. Hope that made sense.
Perfect. Thank you so much, Dean. I'm actually going to start at the bottom from the questions. And so the next one is, are there use cases where it makes more sense to download the data entirely locally? The trade-off between the increase in internet usage versus saving download time.
I think that's up to you to decide. I gotta be honest, when I got my PhD, sometimes it just felt better to have the data locally. Like it just made me more comfortable. The more I use the virtual data set technology, the more convenient it is. It's like up to you if you want to like download, tens of terabytes of data. But I think like we showed, right, like at minimum, if you just need a subset of like an 11 terabyte data set, you can at least use the virtual data set technology to get that subset quickly and then download it as a single netcdf file. So that's going to be your decision.
All right, appreciate that. Oops, sorry.
Well, let's weigh in quickly here that another advantage is that we're looking at strategies to operationalize the creation of these virtual data sets so that we append new information as it comes along. So if you are in the download model, then you also have to, like, say every day or every week, go download new data and add it to your local archive versus in the virtual model, but that will be all available for you to reference as soon as it's created.
That being said, we are not at the point where we're creating like forward streaming, actively being updated virtual data sets, although that is something that we're aiming to offer.
Right. It's on a roadmap.
All right. Well, thank you both. Okay. So the next question is, all these examples are on unprojected data, for example, in longitude, latitude, space. Can you project the data into a different project, for example, the North Pole, before running the processes? I guess my question is, if I run a process on a VDS, do I get a VDS in return if I perform a geometric correction?
No. You should, once you actually process the data, then you should have it locally, like in memory. Now, that's a very general statement, but yes, you should be able to reproject the data, and it's not just then going to be this like virtual data set lazy loaded. It's going to be actual like real values.
Okay, thank you, Dean. The next question is, I guess this stands for library, but does the lib or have non-blocking API functions?
I wouldn't know that actually. Mike might know that better than me.
I don't have the best answer for that question. What I will say is that when you're doing, maybe concatenations or some selection properties, they're rapid because they're being processed on the VDS itself. But at some point you have to get the raw data to do like a mean or a summary or plots. And at that point, you really can't move forward until you have the data. And so you even if it was asynchronous, you could only get so far in your processing. The libraries are going to have their own versions of these things, but for the most part, what we've seen is you can get pretty far along the selection process, and then once you actually want to do some computation, that's when things become blocky, and you click go, and maybe you go refill your coffee, and you come back and you have it. but it's not like you have to wait hours and hours usually for that blocking call at that point.
Okay, excellent. Thank you, Mike. Appreciate that so much. The next question is, do you know if PO.DAAC has virtualized data sets? It would be very helpful for working with the hyperspectral paste data.
I don't know if they have it yet, although I'm trying to remember who I was in contact with, but
and I could find out about this too from Morgane McGibbon. We just had a science team, like a 2-day workshop with the science teams. I can certainly follow up unless you have a different point of contact for that, for the pace.
No, thanks, Jennifer. Yeah, please do that. Whoever asked that question, also feel free to email me to give me a reminder. But I mean, short answer is I don't think they do, but longer answer is that we have been, through like Earth Access, hackathons and stuff, been talking with other DACs, and we know that they're also very interested in this technology and are working towards it.
All right. Thank you so much, Dane. I'm just going back up to the top here. I think I might have to hop back up to the chat. I think quite a few of the questions we are in the extended Q&A.
Yeah, thanks again.
Right. Yeah, just trying to make sure I'm not missing any that have not been responded to. Let me hop back up to the chat here and see.
Well, while you're looking for another question, I just wanted to have another comment on the level Ocean Color,
of course,
virtual data set. Yeah, I mean, as I alluded to in my plot, it would have been fantastic to have like an Ocean Color virtual data set to overlay with the SST and the other parameters and stuff. And we're hoping this webinar will pique the interest of other DAC representatives to virtualize some of their data sets and make them publicly available. Because really, it's the onus on the data curator, the data provider, the data archiver to create these things and then evangelize them and get people to use them.
Well, thank you for that additional feedback. I'd really appreciate it to just put those out there in case there's any additional discussion for this. So the first point was from a webinar, perhaps from a webinar participant, perhaps the salinity is not controlled by upwelling. For example, you could have a seasonal cycle of precipitation that is out of phase with wind jet, and a follow-up. And Jorge, I'm not sure what you mean by, maybe this is a shorthand that I'm not familiar with. It might mean prime PME. Possible reason for the lag with salinity is that cooling takes place for 2 reasons: cooler winds and upwelling, while salinity changes strictly due to upwelling, thus a lag between when upwelling starts and the water reaches the surface. So I wanted to put that out there.
Yeah, thanks for those. I'll comment on those. Yeah, thanks for the insight. There might be some precipitation effect that we're not looking at, so it'd be great to get the precipitation data. But I mean, the salinity and the ocean vertical velocity, they're driven by the same processes, right? And so they're not aligned in these plots. The salinity is lagging even the vertical velocity. So that's a little bit disconcerting. And again, maybe there's some model artifact or the fact that it's not actually a surface signal that I'm plotting, but it's a 5-meter depth. And it would be great to look at other data sets in relation to what I've already looked at here. Say the satellite SMAP derived surface salinity. We do have a virtual data set, but it didn't quite overlap with that time period that I picked. But it's food for further thought, grounds for further research to start digging in and really try to see what's going on with the salinity signal there. But yeah, great points by both Jorge and the other participant. I forget his name.
I think it's Tom. All right. So I do have another question for everybody here. The next question is, are the datasets from the PO.DAAC server stored in NetCDF or Xarray format?
Sorry, you cut out for just a moment. Is the what stored in NetCDF?
Oh, so sorry. Can you hear me now, everybody?
Yeah. Might have been on my end.
Okay, perfect. Are the datasets from the PO.DAAC server stored in NetCDF or Xarray format?
NetCDF.
All right, perfect. Thank you. All right, let's see. Looking down here in the Q&A, see if I have missed any questions, and I don't think so. So let me conduct one quick last check. And I don't see anything. So with that, I'd like to thank all of our speakers this afternoon, and thanks so much for our panelists for joining and for those excellent responses to the questions. And really, even more than that, thanks to all of our participants for joining us this afternoon. We really appreciate your thoughtful input, and reflecting some of your user needs and your feedback on all of this. It's super helpful in determining future webinar topics. And so thanks to all of you. And with that, we'll log off from the audio component and leave the virtual meeting space open an additional 10 minutes. All right. Well, thanks so much, everybody. Thank you, Mike and Ed. Thank you, Dean. And thanks to my backup host there, Joe.
Welcome. Appreciate you all for joining. Please reach out.
All right, everybody. Take care now. All right. Goodbye.
Bye.